Good afternoon, everyone, and thank you for attending our NextGen Wolf Products powered by Nvidia webinar. My name is Lindsay Chapman. I am the Senior Director of Sales at Wolf, and I will be your moderator today for the presentation. We're excited to announce our 7 new products that our CTO, Greg Maynard, will be presenting to you in just a moment. But before we get started, I do want to mention that all our data sheets and product information supporting the products that are announced to you today will be available online at wolf.ca in the coming weeks. If you have any questions, we'd love to hear from you and ask that you speak to your Wolf representative or contact us directly after today's webinar. Without further ado, I'm pleased to introduce our CTO, Greg Maynard.
Thank you very much, Lindsay, and welcome everybody. I know that, well, thank you very much for taking the time to be with us this afternoon. I know that in the past year and a bit, we've probably attended about 10,000 webinars, so I really appreciate the awesome turnout. Okay, so today, I'm going to spend a little bit of time, not too much, just refreshing on what Wolf is all about, just so that you guys get that sense. Then we're going to dive right into our announcements. So it's about the Nvidia Ampere architecture and what that brings to sort of a tactical edge environment. Nvidia Mellanox ConnectX 6, which has some pretty cool architectural improvements and implications. And then we'll go through each of the 7 products in a little bit of detail. You know, again, as Lindsay mentioned, there will be some data sheets and postings online as we move forward over the next few weeks. And then there'll be additional product informations that we'll release as we get closer to ship dates for all of them. And then I put at the back end, if time allows here, I wanted to share a couple of additional references just relating to NVIDIA technology and kind of next steps pieces. So high level, Wolf is 100% laser focused on high performance embedded compute, sensor IO processing solutions, and it's all focused on extreme tactical edge. So nothing we do at Wolf is commercial or benign environment. Everything is high shock and vibration, high temperature extremes, and many constraints, big challenge, which we enjoy. So that's where our focus is. What you can see here is basically the typical applications we find ourselves in, kind of everything from really high performance electronic warfare, you know, or radar processing applications, video processing, right down to autonomy. And so obviously the innovations that come from NVIDIA, they're basically leading the charge as far as AI inferencing, or sometimes we just call that autonomy processing type applications. Capabilities range everything from completely focused on compute to standalone system on module SBC type solutions, right on down to sensor IO. And the typical interfaces we deal with, we're in headless systems, right down to systems that have high density digital and analog IO. And you can see the typical deployments that we find ourselves in. So one of the very big things that are important to us is to align ourselves very well to the open COTS and specifically SOSA initiatives. And so pictorial here just basically shows kind of how SOSA is interconnected. It's driven from the DoD's MOSA initiative, which is a multi-branch initiative intended to pull open standards together into a sort of a unified solution. And with SOSA in particular, why that's important to us is SOSA does a lot on the modular side for us as far as defining the type of ICD, the software interactions, the backplane topologies, and it actually makes it at the system level a little bit simpler in that it reduces some of the choices that were available before in some of the open standards. And so Wolf is 100% committed to open COTS, and we are even further committed to the SOSA initiative. We're part of the working group. We have change proposals in play, really like where the architecture is going, and as you'll see, the solutions we provide, I believe, connect extremely well to where we need to go. And as far as relevance goes, I do see least in the opportunities that come across my desk, there's usually requirements for MOSA initiatives and SOSA in particular. And so that's why we are doing what we are doing, is basically trying to provide those solutions for you. So one important thing to note on conformance, SOSA at the moment, we state that we are SOSA aligned. Our commitment is to make these modules be SOSA conformant, and that's a process we'll be undertaking in 2022, and we'll provide you updates on that as we go. And just high-level observations on SOSA. We're going to be leveraging things like the AMPS string, which is a way of defining how the module will connect. I do very much believe that NVIDIA's roadmap and the developments that they're bringing to bear are very well aligned with where we need to go with SOSA, and that includes concepts like distributed processing and cybersecurity, which for good reason are very important. So NVIDIA Ampere. So this is the latest generation embedded GPU released from NVIDIA. It was released a little while ago. If you listen to NVIDIA's webinars and Jensen, but this is the announce of the GPUs targeting military, aerospace, and defense applications. So these are the ones that we, Wolf, ruggedized for harsh environment. And so this is the latest and the greatest. Significant improvements across the board. I won't go through all of them, but essentially, the amount of cores in the architecture is greatly improved because of the processing is reduced, and so we can fit more in the same space. There's some architectural improvements that basically allow more instructions to be run in parallel than in the past, and there's enhancements along that sort of software efficiency, you might think of it, that end up having drastic improvements. And so at the end of the day, what it really means is you're roughly seeing about a 1.8 times overall compute performance per slot when we think about a VPX card slot, for example. So it's quite significant. And so I'm very excited about what's happening with this technology and how we're able to apply it. It's going to make a drastic difference to the amount of sensor data that can be processed. Latency is going to be impacted by that. There's some reliability enhancements, and it's just all good news, basically. On the other front, so while we talk at Wolf a lot about GPUs, we're now starting to talk about NVIDIA LAN and InfiniBand technologies. And so the ConnectX 6 is something that we'll be talking about today. This device basically adds multiple ports of high-speed LAN. 100 gig E is what's possible today in VPX. We can push that further in future, 200 gig and beyond. We can do that with InfiniBand, and there's some future capabilities there that are quite interesting. And so the bottom line with this is it really will extend, and you'll see as we kind of go through this presentation, it gives some more scalability options, more flexibility at the system level, so we can solve problems in a more efficient way and for more applications. And as far as data flow, as the sensor data set increases, obviously we need to move data more efficiently through a system, whether that's higher rates or connecting more points. And so this ConnectX technology greatly helps with that. So this is a high-level view of the 7 modules we'll be talking about today. The Ampere 3 VPX, the Jetson Xavier 3 VPX, XMC's Ampere, and 6 VPX cards. So starting with the 3 VPX, this is we call this the Wolf 1448. This is the first module that will ship from Wolf with an Ampere GPU. And basically you can think of it as sort of the highest performance possible that you can get in a 3 VPX slot. And so it does not have any other capabilities except full focus on the GPU and squeezing as much performance out of that as we can. As I stated before with Ampere, it's approximately 1.8x improvement. Personally, I believe that will be conservative when we come to characterizing this in our final configurations. And the reasons for that are because of some of the other enhancements we've made that were not talking about today, but we will. That will extend the VPX capability further than we have been in the past. So it'll be more than just architectural improvement. This is the first GPU module from Wolf that has a native PCIe Gen 4 interface. It's not our first time providing a Gen 4 fabric, but it's the first time the GPU also has a Gen 4 capability. And so from just a overall throughput and contention standpoint, that's important. The module comes with SOSA and OpenVPX aligned options, just like before. So that basically means we can configure the module for OpenVPX applications where PCIe resides in the top half of the P1 connector, or we can target payload profile for SOSA aligned solution and target the bottom part of that connector. This will also be the first deployment of what we call Wolf Advanced Metal. And so this is an advanced cooling technique, which I'll talk a little bit about, not too much detail, but I'll talk a little bit about that later. This is also one of the reasons why we believe strongly we'll be able to get above this level of improvement. And another big one for us is this is the first GPU module we'll ever provide or have provided that can go above an 85 C cold wall. And so when we start thinking about more extreme environments or less efficient systems, there's some advantages there that are quite important. And then perhaps most importantly of all is if you're already working with the Wolf 1348, this one is ICD compatible. So you should be able to just drop it in to your existing system, configured the same way, and you're off to the races. In fact, even the Nvidia software drivers available today are compatible with this GPU as well as the Turing GPU. So it's theoretically possible that you wouldn't even have to update your driver. So here's the really exciting part. So this is where we've combined Ampere, that last module, but we've put in a ConnectX 6 Mac controller. And so basically, this is the first time we're providing a module that combines GPU and LAN all on one VPX slot. It's targeting the payload profile. So we're basically fully loading a 14.6.13 profile. So 16 lanes of PCIe, usually bifurcated up into four-lane interfaces so you can connect to other devices, as well as high-speed LAN interface, which we can drive up to 100 gig on the connector. So really with that integrated ConnectX NIC, the concept of GPU direct is quite important. So in this case, low latency GPU direct can mean two things. It can mean over the PCIe bus, we're doing a peer-to-peer connection, and that's one typical connect that we do every day, but it also applies equally to the LAN interface. And so data can come in on the data plane and directly DMA from device to device. And because it's an Nvidia end-to-end solution, it's extremely efficient and low latency because the hardware works together very well and the software obviously connects those dots very well. And so this also opens up the concept of distributed processing architectures. So you have different ways that you can connect sensors to system. You don't always require PCI Express on the sensor, or you can connect systems utilizing the LAN interface only, and so it just opens more possibilities. And this is, in my opinion, this is where industry is going. So this is a really important advancement. And then obviously with the fabrics being fully utilized to the backplane gives us an enormous amount of throughput capability on this module. So technically we can get 32 gig into the module to the GPU, but we can actually go higher than that if we're considering sending data to other profiles in the system. So just a significant amount of data switching and capability here versus what we've done in the past, more than double the speed. So just some examples of some applications this might be useful. You could think of like a RF Vita49 packet processing application where your sensitive data is basically streaming over the LAN interface for the GPU to process, reducing the latency on any IP sensor Doesn't have to be RF, it could be any IP-based sensor. There are next generation LAN and security capabilities that come with ConnectX and Nvidia's software stacks. Because there's so much fabric switching capability here, in many cases, you can probably eliminate the need for a fabric switch in your system. Depends on your architecture and topology, but this provides that type of capability as well, which is important. It might allow you to reduce your swap, reduce your cost. There's possibilities there. And then just on the scalability and flexibility side, this will enable more efficient architectures than what we've had in the past. And the best way to make all this work really is on the software orchestration of that. And so, as you'll see slides ahead, NVIDIA is extremely strong on the software stack and the orchestration of processing nodes. And so we get to leverage those benefits in this hardware. So that was the discrete GPU. You can think of that as kind of like the highest performance per slot possible. This is a little bit different thing that we are doing. This is based on the Jetson AGX Xavier. And so why this is really cool is this is NVIDIA's AI robotics system on a chip solution. And what we've done is we've basically taken that and ruggedized the hell out of it and mapped it into a VPX ecosystem. It's SOSA aligned. We actually currently ship what we call the 12TP. That's a SOSA aligned Xavier module that ships today. This one takes that and then marries it with the ConnectX. And so this one's targeting the SBC IO intensive profile, which gives us some capabilities I'll talk about in a second. It upgrades the buses to PCIe Gen 4, again, really important for throughput and switching. ConnectX gives us those high-speed LAN interfaces. The board support package that's loaded onto this is based on NVIDIA Jetpack. So Jetpack 4.6 brings some capabilities such as secure boot. It also supports the Jetson Xavier Industrial, which is a newer version of this module that is included in this product, and that can operate at a 40-watt power envelope, which is a little bit higher baseline than was previously available in this form factor. We've also included some optional FGX sensor IO. So this allows you to use the IO intensive part of the profile to get not just USBs and additional video output ports, but you can also drive some of our SDI or analog videos out or SDI capture into this card. So what we just looked at was the IO intensive version of the module. We're also offering this in a payload profile. And so in the payload profile, having a completely standalone processor node, we believe is extremely valuable. It enables a lot of capability to scale a system. So basically the way this works is the same as the last module. Jetpack is loaded into the card. It's based on Ubuntu Linux distribution, and you run your applications right on the module. And you can basically connect sensors either through the high-speed LAN interfaces that we've provided or to the 16-lane up to PCIe Gen 4 connections on P1 and P2. So fully loading the payload profile again with all that fabric options. So 16 lanes at Gen 4. Again, the low latency GPU Direct that's available and working with Ampere is exactly the same in the Jetson world. It's a software enabled feature that is hardware accelerated. So there's really nothing that you need to do special to make use of it. And there's plenty of samples and things on how to measure and make sure that that's meeting your performance needs. Obviously, a big part of this module is that ConnectX interface. So this is the highest speed LAN port that we've done married up with a Jetson so far. And so that's quite interesting. This particular module is also, as we go forward, because the ConnectX has the 200 gig capability, this is something that we will be talking about with some select partners on what can be done on that front to interface that in a system. It's definitely a challenge, so that's something that we're kind of working towards. And then what's really great is because this is a standalone module, of course, it's even easier to be scalable, because you can just, it does not require a CPU to be connected to it. It is its own ARM processor CPU. And then the last thing that I wanted to talk about on this connection is what's called multi-host technology. Not going to get into deep detail on that today, but essentially it allows you to connect multiple CPUs to this module. And it's in the past, we've sort of talked about non-transparent bridging and some of those capabilities to connect multiple systems together. And this is a different way to do something approximating the same. So when we release a little more detail on the implementation of this, it will give you some other abilities to move data between systems. It's quite interesting. And this is just an example, of a connection topology. So on left side, Jetson plugged into an SBC slot married up with a payload sensor is one configuration, and the other configuration being payload and payload married together. You can obviously have multiple payloads married together. This is just a simple rendition, and those things can be interconnected depending on your application requirements and topologies. You can decide how to connect data planes, expansion planes between both. And the intent is that from our perspective, what's being made available is both interfaces at full speed. So moving on to the 6U card. So a lot like the 3U 1448, this is the next generation 6U high performance embedded compute module from Wolf. Again, we're leveraging the A4500E. There's two of those that will be down on module. And for us, this is similar to the 3U in that it really is the absolute best performance that can be achieved in a 6U profile. Again, the Ampere brings it, the 1.8 improvement in performance per slot, just due to the architectural software and design improvements that are being made. The module's available in SOSA aligned 6U VPX profiles. So really what that means is that we're leveraging combinations of optional user IO where it's available, but we're also mapping the display port onto P4 where SOSA defines that it can be, so that it can basically drive a display in a SOSA aligned system without having to do anything proprietary or custom there. Because the GPU is native PCIe Gen 4, it's actually a very big improvement in a 6U architecture. So in the 6U world, we're usually not as constrained on having wide bus connectivity. So you can see here, we've got two 16-lane PCIe buses. A lot of the time I'm seeing both of those connected. And so that means you can have a lot of data coming in, and having the native Gen 4 PCIe connection then is really important, because we have lots of data coming in. We want to push that to the GPU. So from an efficiency perspective, this will make a very impactful improvement. Same benefits with low latency GPU direct. Obviously, that's critically important as we connect more and more sensor data in the system. One of the things I didn't really mention on GPU direct is that its main intent is to limit CPU utilization. That's one of its goals. So the CPU doesn't have to manage the transactions, and so you can free up some resources to do some other things. Obviously, in the case where you have so much data traffic coming in, that's even more important. And a lot like the 3U card, this one is ICD compatible to our Turing 6U VPX module. And so just as easy as an upgrade path on that front. And just some common topologies in 6U world, we do typically see that you may have a setup where you have one CPU master root complex. Also see frequently having two root complexes, one connected to P2, one connected to P5. Also see sometimes where we might use P5 as to daisy chain into additional modules for processing. So we thought that's the big one, and then a 60 VPX envelope is quite big. So now we're going to the other side of the spectrum, small form factor XMCs. So this one, again, this is for us the best in class that's possible in a small form factor. It's based on the A2000E from Nvidia. And so in this case, we're actually coming from the Wolf Pascal XMC. So we got a couple architectural improvements. And so we're looking at least a 2.5 improvement versus existing technology. PCIe Gen 4 is available here. The reason why I say available is because the system interoperability, that's something that we need to work together with because the connector interface is not rated for PCIe Gen 4 unless you move to ANSI Vita 88, which I'll talk about in a second. One of the use cases we see a lot of in the XMC world is using the encoder-decoder capability of the GPU. And so in this case, NVIDIA has added some enhancements. There's a new encoding mode, and there's a little bit more efficiency, which means that you can process more streams simultaneously a little bit than what you could do in the past. I mentioned that Gen 4 requires ANSI Vita 88, so our module is actually configurable and compatible with XMC1, XMC2, and XMC3, as I call them. These are things that are available as factory config options. Just talk to us and we can make sure that we're setting things up the right way. Typically, these solutions are configured for 25 watts as they ship from Wolf. This is because usually the XMC is going into a blade architecture 3 VPX, and there's a limited cooling capability there, and so that's why that's done. But the design is capable of much more than that, and so when we're in other applications, we might be in a larger carrier or an embedded system, we can basically crank this up according to your environmentals and your system capabilities. And then finally, I mean, as far as upgrade path goes, we're very committed to try to maintain steady ICD, and this one is ICD compatible with the 3176. So then the next XMC that we're announcing today is the Wolf 3470. So this one is the A2000E, and we've added the Wolf FGX to it. And so this is actually an FGX2. So not only do you get the 2.5 improvement for processing that sensor data, but we're also adding higher speed SDI than we have in the past. This one will go up to 12G SDI capability, as well as the analog channels. Our driver that we've built for the FGX is low latency. So it's really good at basically moving the data from when it comes in through switch directly to the GPU for processing. So a lot of the data flow can actually be done within the module itself without having to drive out and bottleneck or tax a system. And so this is really excellent for SQAP constrained environments, for example. This is also the first time we're going to provide a stereo audio capture capability. So that's something that will be available on the platform. And this one as well is ICD compatible with our Pascal 3177 and 3170 module. Okay, so that's the 7 products. I did want to quickly touch on a couple of other topics that are related to that. So one of them is our FGX sensor IO products. So in the last year, we have developed some new capabilities as it relates to combining Nvidia GPUs and Wolf FPGAs for sensor I/O connection. One of them is the FGX2. We call the product 3183. So this solution provides you up to 8 channels, which is something we've not done before. We've been limited to 4 channels in a XMC package. So we're basically driving 8 up to 12G SDI, combinations of analog. We also have DVI as a capability now. That's a new one as a COTS offering. And so there's a couple different architectural choices, 3 VPX, XMC, depending on your I/O mix, price point, power level. So talk to us about that, and we can certainly find the right fit depending on what you're trying to do. And I also wanted to sort of reiterate, when you look at the product pages and you see that we're talking about SDI or DVI or CVBS, we do have a fair amount of flexibility in what we can make those interfaces do. And so this is just the cheat sheet of the typical interfaces that we see. So SDI is quite common, so that's usually what we talk about. We can change interfaces to work with Coax Express or ARINC 818. We're doing work with DisplayPort. STANEG 3350 is still a common requirement for us. And so the point is that there's configuration choices there. And so keep that in mind, because usually the sensor I/O side is kind of a unique recipe depending on the system, and we can accommodate that. Okay, so Wolf Advanced Metal. We will be releasing a lot of details about this and what's possible around this next year, 2022. What I wanted to just touch on really quickly was just to get the concept of what we've been able to achieve. So this solution basically is very good at optimizing the thermal distribution. It's done by a design technique that we've worked on actually for the last 2 years at Wolf. And why that's important is it simply reduces the thermal resistances in the design. And so there's a lot of, and when we do that allows us to do things like improve reliability, tune a little bit better for efficiency in the system as a whole. Weight reduction is a pretty big deal that we that's a problem we all have to face, and that's something that we've been able to tackle a little bit here. Depending on the product we're comparing, we've got a 12 to 25% sort of improvement on weight, which is pretty exciting. And it's applicable to basically all of the V248 cooling solutions. So we're actually currently working on it on the 1448. That is the first product that will ship with this solution, and that'll be focused on a conduction cooled implementation because that's my view. That's where the kind of biggest ecosystem impact is first, but it's equally applicable to the rest of the cooling solutions, and we'll be working through those kind of as we progress. As far as what we've talked about today, there's our goal is to provide modules that are supportive of multiple topologies without having to have 1,000 order codes and a whole bunch of designs. And so really what I wanted to emphasize here was that we find ourselves working either through PCI Express fabric as the main interconnect between modules, or LAN InfiniBand fabric is becoming more and more available, and that's going to continue. And so the way to think of them is on the PCIe side, if you have a latency issue, we want to reduce the number of switches. We want to use PCIe because that's the fastest, point-to-point connection that we can do, and it's really good at localized processing. As we bring on the LAN and InfiniBand interfaces, as we talked about today, that's really simplifying the software orchestration, how we move data and process data in more complicated systems. And some of the systems that Wolf is involved in today are becoming increasingly complex because there's the challenge for the tactical warfighter is actually increasing a lot, and it's driving the need for a lot more processing. And so I think the LAN InfiniBand fabric is very good at simplifying that problem, which is really can be summed up as like a distributed processing kind of model. And what we've talked about today, what I've shown you, is actually compatible with both of those fabrics. So no matter what way your architectures are going, we have a SOSA aligned solution that can plug into that architecture and give you the best bang for the buck. That's really what we're trying to do. There's just some examples of some of the interconnect topologies that we typically see. Okay, so we don't have time to really dig into too much on the software side here, but at the end of the day, as good as all the hardware enhancements are, what really makes this very efficient and work really well is the software stacks that drive it. And fortunately for us, Nvidia is very, very good at building a software framework, right, and supporting it through all the different bits of hardware that we've shown and providing that life cycle. So whatever you're investing now in, you know, your software application development, your architectural choices, Nvidia supports that for many years to come. And so your investment is protected. As you get new hardware, you can plug it in and your software from an older library will continue to run. And so I wanted to highlight a couple of those key SDKs just to kind of tease the idea of understanding what's possible. So NVIDIA Rivermax, this is a unified framework. It's basically trying to optimize data and sensor streaming over a network that needs to be processed by a GPU. And so if you go online and you look it up, you'll see that you know, they talk a lot about broadcast video, but it's equally useful and important for any type of data. It doesn't matter what it is, as long as it's a streaming application. And so what makes it really cool is it's focusing on zero copy to the GPU, meaning it's just one transaction, not multiple. There's enhancements in the software, as there often are. So kernel bypass basically means it's skipping some of the middleman steps. It comes with some timing and synchronization, which is extremely important in, say, RF and communications applications. And really the beauty of it is it's a unified framework that kind of connects it end to end for you. So this video is basically showing the sensor data comes in with payload information and headers or metadata. And basically the ConnectX is splitting these without any software or CPU overhead, so that the CPU only receives the metadata information that it needs to process, and the GPU receives the meat, the payload that it needs to process, and there's no data mixing around required. And so it's just an example. We do have some links you can read up about this online, and absolutely reach out to us if you have any questions or you want to talk about this one any further. The other one, other couple concepts I wanted to hit on real quick, CUDA 11. So CUDA is the fundamental SDK, obviously, behind how we accelerate hardware accelerate math operations with the GPU. And so all the sensor processing, or a lot of it, is done through a CUDA framework. And so NVIDIA's approach is that every year they're releasing a new CUDA package, and there's releases throughout where they're incrementally updating. So what I wanted to call out here was just with the latest CUDA 11 framework, which really is the fundamental SDK to what we're using to solve problems. They've introduced a new data type, and so basically that data type, it's bfloat 16. High level, it enables a little bit less precision, but really good math results. And so that ultimately lowers the bandwidth required, lowers the memory requirements, and just makes the algorithm that's being processed, or the inferencing, that much more performant. So why it matters, if you look in this table here, this is a double, floating point 64-bit data type. that's the number of operations per clock that you can achieve, 128. As we get down into where NVIDIA has optimized, or architecturally optimized, I mean, or data types are shrinking, we get additional operations per clock. And so you're starting to trade off a little bit of precision for a lot more performance. And you'll be able to play with that with the latest SDKs. You can see there's some experimental data types as well, where we get into really low, really small data types and accelerating those to get a massive amount of operations per second. So that's just a continual evolution, that as we get more and more hardware architectural enhancements, we're also getting software enhancements at the same time. So we kind of get a double hit when we talk about performance improvement. We talked a bit today about GPU direct RDMA, just showing you in a typical kind of PC world, because it's maybe a little easier to visualize, how these things would connect. And so you would have one example would be having a GPU, having a CPU. This is a system with a ConnectX device, and that connects to another system that is duplicate. And you can basically, across this interface, one use case is you can pair the GPUs together and be moving data from this frame buffer to this frame buffer with very minimum overhead on the system. So high level, that's how that interconnectivity works. And there's plenty of resources online to understand, how that operates and how you can, benchmark it and best make use of it in your applications. And then the other interesting one that we don't normally talk about, Omniverse. So this is something that NVIDIA has released for a little while now, and the intent is it's basically a simulation environment that provides you with training capability. So as you're developing like an AI or an inference engine, you can basically simulate an Omniverse to provide the data required to train your model. See, in the past, training the model requires lots of data, and if you can't do it in a simulated environment, you need a lot of data. So sometimes that's impossible to get. Like when we think about, a complex networked mosaic that the warfighter really encounters today, you can see all these nodes are all interconnected. Simulating that, or getting that data to simulate the performance of, say, an RF or a secure communications channel is extremely difficult. And that's why simulation is an amazing solution to that. And I know that Ericsson in particular has done some really good work simulating 5G communication, for example, being able to simulate when signals are under threat or in complex terrain. And so it's very applicable to the problems that we're trying to solve, and it's just another way that NVIDIA software kind of connects those dots. And then the last one I wanted to mention was the Triton inference server. And so high level, this is a architecture that allows you to go from AI training models to inferencing and deploying that end to end. So you can kind of use it anywhere that makes sense in your ecosystem. Specifically to the Wolf world, we're very much focused on the extreme tactical edge, and so it's something that applies to Jetson. It will accelerate the data to Jetson, and it also allows you to split large inferencing models. So this is another one that we get fairly often. We get asked, I have an inference model that's quite large, and do you have a bigger frame buffer GPU available? And this is actually a different way to solve that problem. So the Triton inference server can actually go from capture to detect, classify, and processing, and it can do that over multiple GPUs. And the way it does it is it'll basically split the model up in a intelligent way to be able to chunk out that work. And that's basically what the software enables for you. And so it's also a very interesting solution, especially when you're looking at implementing Jetson at the tactical edge. And so that's another one that I highly recommend you guys read up on. Okay, so I think that, so this is the view of the latest playbook from Wolf, as we call it. So the 7 are incorporated into this view, but you can see that we have solutions for a couple different profiles we didn't talk about today, actually. As much as I don't like switch fabric cards, because they're a tax in a 3U system, there are times where that's the only option. And so we've developed basically a GPU and fabric switch in one, so that we can provide some optional HPEC capabilities on that slot and turn it from a tax into having a little bit of a benefit as well. And then I mentioned the SOSA change proposals. So one of the things that we're working in the working group on is enabling sensor I/O of the type that we normally see, which would be SDIs, analogs, video, et cetera, over the same RF interface that's available in Payload slot. And so that product we call 1349, and that's a product that we actually started shipping early this year. Okay, well, I want to leave you guys with one quick action. We're almost out of time. I'm glad that I didn't run over. That's good. I really appreciate the challenges that you guys bring. I think that I have a lot of I really enjoy engaging at the actual system architect level, understanding your issues, and we Wolf as a team just love finding the solutions. That's really what gets us going. So I wanted to leave you with an action. Absolutely, let's talk. If you have new program bids, new SOSA requirements, things that you're not sure about, let's set up a technical one-on-one. Happy to go through any system and data flows that you want to share with us. We can then help you sort of pick the right module. We can talk about the right Nvidia SDKs that you might want to look at and use if you're not sure, and really want to engage at that level. I think there's a lot of value there, and that's how we've been succeeding here at Wolf for the last several years. That's really part of our success. And then the other thing that I want to highlight is just that as far as making the right software connections, happy to get connected with the right software experts for whatever architectural challenge you're trying to solve. And so that's the open invitation, contact information at the bottom. And I look forward to hearing from you guys. And that's it. So I think at this point, thank you very much. I think, I wanted to say that in this day and age, time is extremely important. And so I'm very happy to have given you back 10 minutes this afternoon. So thank you for taking the time. I really appreciate. Please reach out, as I said. And as we go forward into 2022, you now see the roadmap of what we've announced and released, and you will see some additional details from us as we proceed. So thank you very much, and let's talk soon.